If you've ever taken a conducting pipe and dropped a magnet down that pipe, then you would observe that the magnet takes a lot longer than you would think in order to travel the length of the pipe. And again, this is a conducting pipe, not a magnetic pipe. And so it's not like the magnet is sticking to the side of the pipe, but there's another reason why the ability of the pipe to conduct a current might cause the magnet to slow down while it's falling through it. In order to understand what's happening between the conducting pipe and the magnet, we need to first make sure that we understand Faraday's law. Faraday's law says that a change in magnetic flux induces an EMF in a loop of conducting wire. So here you could imagine that the pipe kind of acts like a big loop of wire. And if we were to take a closer look at the magnet, then say the south end of the magnet was dropped in first. So the diagram I have on the left shows the magnet falling towards the bottom of the screen, and the magnetic field around that magnet might look something like this, where magnetic field lines would appear to be coming out of the north end of the magnet and going into the south pole of the magnet like this. And so let's consider a point on the magnet, right? Let's consider maybe this point here. And if we were to draw a dashed line going across the pipe, as the very top edge of the magnet moves past that green line, the magnetic flux would be high because we're close to the pole of the magnet. And as the magnet continues to fall, that green line would become further and further away from the edge of that magnet. And so the magnetic flux at that point would be decreasing. And similarly, you can imagine a point at the bottom here where if we analyzed this particular green line, the south pole of that magnet would be getting closer and closer to that green line, which would mean that below the magnet at that green line, the magnetic flux would be increasing and increasing. The key here to begin with is to just note that above and below the magnet, the flux at any particular point would be changing. Right? So if you picked any point above the magnetic flux would be decreasing, and any point below the magnetic flux would be increasing. But the key in Faraday's law is that in the pipe, so long as that magnet is moving, the flux around that magnet is going to be changing. And if there's a changing flux, then there will be an EMF that is produced in that conducting pipe. It's not until we look at Lenz's law that we'll begin to understand the direction of the current and why the current is in that particular direction. Lenz's law says that the polarity of the EMF induced by the changing magnetic flux is such that the current it creates produces a magnetic field that will oppose the change in flux. And I've tried to state Lenz's law as clearly as possible, but even still, it's very complicated. There's multiple steps to understand in Lenz's law. The polarity of the induced EMF is such that the current it creates will produce a magnetic field, and the magnetic field that current produces will oppose the change in the flux that the magnet is causing. And so in order to understand this, we need to go step by step looking at the pipe and specifically talking about the direction of the current, the direction of the field induced by the current, and the direction of the change in the flux above and below the magnet. Let's start by looking at the top of the magnet. Because the north end of the magnet was on the top when we dropped it through the pipe, the magnetic field from the magnet at the top of the magnet, which I'll call B mag, points toward the top of the pipe. And by the way, this is true at the bottom of the magnet as well, right? The magnetic field from the magnet at the bottom of the magnet would be pointing toward the top of the pipe as well. And so if this is the case, then what is the direction of the change in the flux at the top of the magnet. And in order to understand this question, I want to use a little bit of an analogy. Let's think about for a second, we have a car. And let's suppose that that car has a velocity that is to the right. And so this car has a velocity vector that is pointing to the right. In order for that car to slow down, let's say that what we're trying to do in the first case here, I'm going to draw two different cars, is slow down. Then if we have a car with a velocity to the right and we want it to slow down, then that car's change in velocity would need to point to the left. So delta v, which is the acceleration, but the change in the velocity would need to point to the left. And similarly, if we wanted to speed up and we had a car, once again I would draw a lovely picture of a car. And in this case, the car was still traveling to the right, but this time we wanted to speed up, then the change in the velocity would have to be in the same direction. Delta v would need to also point to the right. And so when we want to slow down, the change in the quantity has to point in the opposite direction, and we want to speed up, then the change in that quantity needs to point in the same direction. And so at the top of the magnetic field is pointing towards the top of the pipe, and we happen to know that the magnet slows down, so the change in the flux, delta phi b, should point toward the bottom of the pipe. This is not Lenz's law yet. This is just an observation. We know the magnetic field is pointing toward the top of the pipe. The magnet is falling through the pipe. It's slowing down, so the change in magnetic flux must point towards the bottom of the pipe. What Lenz's law says is that the current produced in the pipe, in the region that we're considering, which is above the magnet, should produce a current that opposes the change in flux. And the change in flux is exactly what I've just drawn in red. And so the magnetic field produced by the current in the pipe above the magnet should oppose that red arrow that I've just drawn. And so what we know so far is that above the magnet there needs to be an induced current that creates a magnetic field that points up, that opposes the change in the flux. So I'm going to call this B IND for B induced. The current created above the magnet should oppose the change in the flux and cause a magnetic field that points upwards. And so what would the direction of the current be above the magnet? We can use the right-hand rule to determine that. For a straight wire, what we've done is we've pointed our thumb in the direction of current and our fingers curled in the direction that the magnetic field was in. We're going to do something similar here, but it's going to be a little bit more difficult to visualize. What I want you to do is start by taking your right hand and having your thumb point toward you, and imagine your thumb being on this blue dot here on the left side of the pipe. Notice how with your thumb pointing toward you, your fingers are pointing toward the top of the pipe, which should be correct because the induced field from the movement of charge in the pipe is pointing toward the top of the pipe. And now what I want you to do is imagine wrapping your right hand around the front surface of that pipe, moving your thumb to the right. As you do that, what you should find, as you move your hand across the front edge of the pipe, you should find that by the time you get to the right side of the pipe, your thumb is now pointing into the screen. So on the left side, your thumb was pointing out toward you, and on the right side of the pipe, your thumb was pointing into the screen, and all the whole time, your fingers are pointing toward the top of the pipe. And so this blue arrow now, which goes from left to right across, and on the back side of the pipe, from right to left, like this, would be the direction of the current above the magnet. And so this blue line represents the direction of the current. I suppose if we were to be looking at this from the top down, we would call that a counterclockwise current. And that counterclockwise current is creating a magnetic field that points toward the top of the pipe. And that induced magnetic field, which is being caused by the changing flux, opposes the change in the flux, delta phi b, that points down. Let's take a look back at Lenz's law and see if what we've talked about is consistent with that. Lenz's law says the polarity of the induced EMF is such that the current it creates produces a magnetic field, in green, that opposes the change in the flux, which is in red. And that is the case. And so now let's see if we can do the same thing for the bottom. On the bottom of the magnet, there's one key difference, and that is the green line at the bottom of the magnet is experiencing an increasing flux, whereas at the top of the magnet it was experiencing a decreasing flux. And this is why I introduced the speed up, slow down metaphor. At the bottom, the change in the flux should point in the same direction that the magnetic field from the magnet is pointing in. And so for that reason, at the bottom of the magnet, the change in the magnetic flux, delta phi b, should point up. It should point in the same direction as the magnetic field. And if that's the case, then you should automatically know that the induced magnetic field will have to point down. So in this case, B induced points down because the induced magnetic field has to oppose the change in the flux. And in this case, if we have an induced magnetic field that points down, what does the current look like below the magnet? Well, in order to create an induced magnetic field that points down, your fingers would always have to be pointing toward the bottom of the pipe. And so I'll draw the same diagram in blue. Let's start on the right edge of the pipe this time. In order to have your fingers always pointing toward the bottom of the pipe, on the right-hand side your thumb would have to be facing you, and although this is difficult, as we wrap our hand around the front edge of the pipe, you would find that if you were able to wrap around to the left edge of the pipe, then your thumb would be pointing into the screen, like this. And so along the front edge of the pipe, the current would go from right to left, and on the back of the pipe it would go from left to right. And so once again, that blue line, which if we were viewing it from the top would look like a clockwise current, is represented in blue there. And so let's see if there's one last thing that we can do in order to kind of make this a little bit simpler. One way that we could understand this instead of all of these arrows is we could think about it in this way. The magnet has its own magnetic field, and as it falls through the pipe, it creates magnetic fields in the pipe. Let's represent the magnetic field of the magnet and the magnetic field it induces in the pipe as just little bar magnets. What I mean by that is, as it's falling through, the bar magnet looks something like this, right? Where the north end is here and the south end is there. And the magnetic field it induces above the magnet looks like this, where it's also pointing toward the top, which means its north end is here and its south end is there. And if that's the case, what you should notice is that there is a south pole here and a north pole here, and those two poles would be attracted. So it's as if there is an attraction between the north end of the magnet and the south pole of the induced magnetic field. And below the magnet we could do the same thing and you'd find a similar result. The magnet itself has a north pole and a south pole, and the induced magnetic field which points down would have a north pole here and a south pole there. And so in this case, on the bottom, the south pole of the actual magnet and the metaphorical south pole of the induced magnetic field are there, and there would be a repulsion. And so there is simultaneously an attraction with the induced magnetic field above the magnet and a repulsion with the induced magnetic field below the magnet. And for that reason, there is a net upwards magnetic force on the magnet. And so if we were to draw a free body diagram for this magnet as it's falling, it has a single gravitational force that points down and an upwards force that is not as large as mg, that is some magnetic force that's a result of the two induced magnetic fields pushing up on the magnet. And what this leads to is the case where the net force is still downwards, but it's not as big as mg. I strongly encourage you to try to go through this whole process on your own. Sometimes it looks like a blur when I'm just drawing it all together. But remember, as the magnet falls, Faraday's law says the change in flux that's happening in the pipe produces an EMF. And the polarity of that induced EMF is going to cause a current. And the direction of that current is going to create a magnetic field that always opposes the change in flux. In order to understand the relative directions of the magnet's field, the change in the flux, and the induced field, I think it's useful for us to look at the metaphor of the car and it speeding up or slowing down. Hopefully this is a good explanation for why if you take a magnet and you drop it down a conducting pipe, it takes longer for it to travel the length of the pipe.